Good evening, everybody. So this is week 3. Let's start for this live session. And my name is Jyoti Sharma, and I'm a PhD student from ISA Bhopal. So let's start with this. Um, Let me open this. Yes. Uh, so today we will cover the week 3 lectures, and these lectures are on chemical kinetics. So we will basically will try to get to know what do you mean by this rate of the reaction, and then what do you mean by activation energy, and how we can solve the problems related to the rate of the reaction, the constant of the rate reaction. So we will try to solve this. So let's start with our first question. Okay, so my first question is, how are the reaction orders M and N in the rate law equation determined? So we have one equation, and that equation is R. This R is nothing but the rate. So rate is equal to K. This is the rate constant. And then the concentration of A raised to power M, and the concentration of B raised to power N. So, and you have to tell me on what factor, how we can calculate this M and N. So we have four options: from stoichiometry coefficient of the balanced chemical equation, by performing experiments and analyzing concentration versus rate data, by assuming M is equal to N is equal to 1 for all reaction, and then from catalyst used in the reaction. So what do you think, how we can calculate this M and N? Um, so you have option A, B, C, D. You people can write in the chat box. You people are always welcome to write and even speak. So what do you think, how we can calculate this M and N? Can we calculate it from the coefficient, or we have to do some experiment to calculate this M and N value? What do you think? Can anybody write the answer for this? So R is nothing, R is the rate of the reaction. K is the constant for this rate, and A and B are the concentration of the reactant. M and N are the orders. So how we can calculate the order, that is M and N? uh, this we can't get from the equation, the balanced equation, but we have to determine it experimentally. So let me tell you first, explain what do you mean by this reaction rate, and then we will go to how we can perform this experimentally. So I have one or two slides for this. So the answer will be by performing experiments and analyzing concentration versus rate data. So what you have to do is, you have the concentration with the time, and then based on that you have some plot. Based on that plot, you will determine this M and N value, the sum of the M and N. So we have a lot of question based on that as well. But let's see first, what do you mean by this reaction rate? So reaction rate is the speed at which reactants are converted into product in a chemical reaction. So this is nothing but the change in concentration of either reactant or product per unit time. So with the time, how our reactant is decreasing, or we can also say how our product is increasing with the time. So the reciprocal is of the time. So the unit will be, you have concentration will be in molarity, and concentration per unit time. So this may be second, this may be minute, this may be hours. So the unit for the reaction rate will be molarity per second, molarity per minute, molarity per hour. So you can change the unit of time, and based on that you can tell the unit of the reaction rate. So if you are talking about this reaction rate in the terms of reactant only, then how you can see? So for example, you have one basic uh, equation, that balanced equation, that is the small a, capital A. This capital A is concentration of the reactant, one reactant, plus B, and the capital B, this is again the concentration of the another reactant, that is B, and this will give to the C plus D. Okay, so if you want to calculate the reaction rate, that is R, so what will be, you have to do it, so this minus is for the reactant, because reactant is decreasing with the time, but you have the positive sign for the product. Okay, and whatever the coefficient you had, you have to do it 1 by A, 1 by B, 1 by C, 1 by D, like this. And then the concentration, how the concentration is changing. So dA, dB, dC, de, dd, and then change per time. So this is dt. So this is like from any of the chemical species, we can calculate the reaction rate, and this will be equal to as per this equation. Okay, and as I told you, negative sign is for the reactant, and that indicate that concentration of your reactant is decreasing over the time. Then okay, then how our concentration rate can be changed. So there are a lot of factor based on this concentration rate can be affecting. The first is concentration of reactant itself. So if it is the higher concentration of the reactant, there will be more chances of the collision, and this will lead to the higher rate. Then temperature. So if you have a higher temperature, what it will do, it will increase the kinetic energy, and as soon as it will increase the kinetic energy, the frequency of the collision will be increased, and even the collision will be very energetic in nature. So what will happen, that will also lead to the higher rate if you are increasing the temperature. Then catalyst, always you know that if we need to speed up the reaction rate, then we have to add some catalyst. So what catalyst does, it lowers activation energy and speed up the reaction without being consumed. Then surface area, more the surface area you will have, that will give you the uh, increased reaction rate. Then pressure, if you have more pressure, then obviously collision will be happen very frequently, and this will again will lead to the increased rate reaction. Okay, so basically in the MCQ question, you had that equation, R is equal to K, this K is the rate constant, and then the concentration of your reactant, that is A and B, and this is power to m and n. This m and n is the order. Okay, so these are the reaction order, and these are not just like the coefficient, but these are the reaction order, and this we can't calculate using the coefficient, but we have to determine it experimentally. So this was just the question, so how we can calculate this m and n. So this we can calculate using experimental data set. Okay. Okay, the next question is, let me clear this. So the next question is, the unit of rate reaction is typically expressed as we already have like learned. What do you mean by this reaction rate? So can you tell me what is the unit of reaction rate? We have four options. The one is mole per second, molarity per second, gram per second, and liters per second. It's with the option A, mole per second. If I will say that this is not mole per second, but this is molarity per second, what do you think? Let me again share you this. Okay, so your reaction rate is the concentration divided by time. Okay, and this concentration of your reactant, this concentration is nothing but the molarity. And molarity is what? Molarity is number of moles per liter. So the answer should be molarity per second, because this concentration of A, the unit of this concentration of A is molarity, number of moles per liter. And then we have a divide by dt. So dt is in second. So what will happen? This will give you the molarity per second. Is it clear? If Smita, is it clear that answer should be B, not A? This is Malati per second. Okay, great. So answer B will be right. Okay, next question is, as I told you, how we can calculate this order of the reaction. But here, if we want to calculate the reaction rate, so we have a various method by which we can calculate the reaction rate. But here the question is, which of the following is not a common method for measuring reaction rates? So the first is quenching the reaction at specific time interval. B option is measuring absorbance or color changes over time. C is measuring property like BOD, COD, or fluorescence. D is measuring the final equilibrium concentration of product only. So what do you think? What should be the answer? How we can measure the reaction rate? So let's say I plot one thing. So here we have C, that is the concentration, and here I have T. So this is time. So with the and let's say this is the concentration of the reactant and this is time. So with time, let's say the concentration is decreasing. Okay, so with the time we have to see the decrement of this concentration. This will give us the reaction rate, right? So whenever we will measure the change in the concentration of the reactant per time, that will give you the reaction rate. And we have to multiply with the constant value. Okay, so how we can do this? What are different method how we can calculate this reaction rate? The first is quenching the reaction at specific time interval. So for example, initially at 5 minutes we were calculating the concentration, then at 10, then 15. So with the time we are calculating the concentration. So yes, this is the one of the method how we can calculate this reaction rate. Okay, so this is the correct method. The second is measuring absorbance or color changes over time. So what do you mean by this? As you know, so here we have another graph, and this is concentration, and here we have the absorbance. More the concentration, more light will be absorbed by that solution. Okay, so for example, you have one solution of NaCl. Okay, so if you have more sodium, or let's say chloride in the solution, so uh, the light that will be absorbed by this solution will be absorbed more if the concentration is more. Okay, so this is how, based on the absorbance of the light versus the change in the concentration over time, you can calculate also this reaction rate. So this is also right. This is also right. Then measuring property like BOD, COD, or fluorescence. So this is like how with the time this oxygen is being utilized by the microorganism, or let's say by some chemical. So how this oxygen is being consumed or oxidized or utilized. So this is again the method how we can measure this reaction rate. So this is also the correct form. But here measuring the final equilibrium concentration of product only is not the option, because for example, again, this is my concentration, this is my time, and this is how of the reactant is decreasing with the time. And if just I have this one, so based on this one, I can't calculate the reaction rate. For reaction rate, I should have value here, I should have value here, I should have value here, so that I can get to know whether my equation is linear in nature, quadratic in nature. So based on that only, I can judge what
Lakshman
kind of
madam.
reaction rate it is. So my D option will be right. So this is not the method how we can calculate this
Present.
reaction rate.
16 present
So
madam.
Right answer. Okay. So here is the explanation. Reaction rate are determined by tracking how concentration change over time. Measuring only the final equilibrium concentration does not provide rate information as it does not capture the reaction dynamics. That's why this D answer is the right one. Okay, next question is, why does the slope of the tangent line represent the instantaneous rate of the reaction? So what it is saying, again we have concentration, we have time, and this concentration is reducing with time. So it is saying this is so if we want to calculate the reaction rate here, then we have to draw a tangent line. Okay, and this tangent line will give you the slope value. So the question is, why does the slope of the tangent line represent the instantaneous rate of a reaction? So I have four options. Because the tangent line touch the concentration versus time curve at only one point, showing the rate at that exact moment. B is because the tangent line passes through 2 points, showing the average rate over time. C is because the tangent line represents the total concentration of the reactant, and D is because the tangent line is always horizontal for any reaction. So can you give me the answer for this? Why the slope of the tangent line represent the instantaneous rate of the reaction? Um, B. If Smita, you have to understand once again. This is instantaneous, not the average rate. I will discuss. You don't worry about this. Anybody want to give me the answer for this? Why does the slope of the tangent line represent as the instantaneous rate of the reaction? You people can write in the chat box. You people can also communicate with me. Unmute yourself and you can write. So what should be the right answer for this question? A, B, C, D. Okay, so the answer should be A. Let me tell you why. So as I told you, so we have the concentration, we have the time. Okay, and here there is only just one point, right? So the concentration, let's say at after 5 minutes. So after 5 minutes, what will be the concentration? So this is the instantaneous rate. Here, let's say after 10 second or 10 minute, what will be the concentration? So this is just like that. When you are driving, you have the one header. From there you can see how our speed is changing, though. So this speed is very much similar to the reaction rate. So your speed is like always with the time it is changing. It is 30 kilometer per second, then it is, let's say, 35, then it will go down, it will come to the 20 kilometer per second. So every minute, every second, your speed of your bike or the car is changing. So just like that, instantaneous rate of the reaction is just like that. With the time, or concentration of the reactant will be changing. Okay, and if we are drawing some tangent line. Okay, so the thing is, if you have something, let's say if you have this one, and here you have drawing one tangent, so tangent will be only 1 point, right? So this tangent line will give you so this tangent will be at only 1 point, and this 1 point will give you the concentration at a particular time. So this is not average. And if you want to calculate the average, so let's say again you have, let's say, this curve. and here you have something, here you have something, and then you are drawing a line here. This is not tangent, but this is a line. This line can give you the slope, average slope, or this will give you the average reaction rate. Okay, but if you have this one and if you are drawing the tangent, this will give you the instantaneous rate. Okay, so that's why this first will be right. This will not be the right because tangent line doesn't pass through 2 point, but it passes through 1 point, right? And if tangent line will pass through 2 point, just like here, here, and here, this will give you the average. Because the tangent line represent the total concentration. No, this is not right. Because the tangent line is always horizontal for any reaction. This is not right because tangent line can have any angle. Okay, so that's why this A will be right. Okay, next question is, it is a difference between molecularity and the reaction order. So you people know that. For example, if we have this A, B, sorry, this is our reactant, and this reactant is giving to, let's say, B and B. Or let me add something here. Just let me erase. So if you have one reaction B and B, and this is giving you C and let's say C. Okay, so this is your reaction. And here, the thing is, your reaction is equal to K, then A, and we have B, and here we have to raise to power M and this N. Okay, so from this, this is kind of base. So you have to tell me the key difference between molecularity and the reaction order. So first option is molecularity is determined experimentally, while reaction order is theoretical. The second is molecularity refers to the number of reactant molecules involved in an elementary step, while reaction order is determined from rate law. C is molecularity applies to overall reaction, while reaction order applies only to elementary step. D is reaction order is always an integer, while molecularity can be fractional. So what do you think? What is the answer? Let me see the chat box. People have given me some answer. Dharmika gave me B answer. Then Lakshmi also gave me B answer. Yogi C, and Mohan told me, okay, ma'am. Okay, this is not the answer. This is just okay. Okay, so just try to understand from this one. We have A, this small a, and this small b. So these are like number of molecules of A that are reacting with the number of molecules of B, and this is giving the number of molecule of C. So, this coefficient will give you molarity. Okay, and here I wrote an equation. Here R, this is the reaction rate, and this is the reaction constant, and M and N. So these are the order. So these are the reaction order. Okay, and in very first question, what I told you, this M and N we can't calculate from this small a and small b. We have to derive this experimentally. So this M and N are nothing but the orders, and this order we have to estimate experimentally. But this A and B, uh, finding out the number of molecules we need that will collide to each other, and that will give rise to number of moles in C. Okay, so this we can calculate theoretically, right? So what you can say is that molecularity we can estimate theoretically, but this m and n we have to calculate experimentally. Okay, this is the one thing. Then second thing is, so based on that you can remove some of the option. Then second thing is, this m and n, this because we are calculating experimentally, so this can be whole number, this can be fractional number. Okay, but this a and b will be integer, right? So can now can you tell me what should be the answer for this? So B is the right answer. Molecularity refers to the number of the reactants molecule involved in an elementary step, as I told you, while reaction order is determined from rate law. So most of you people gave me the right answer, and this will be the only answer. So here is some justification as well. Molecularity is the number of molecule that collide in a single elementary reaction step, and this will always be an integer, and reaction order is determined experimentally from rate law, and that can be fractional or zero in the complex reaction. So from here I think you can tell which one is the right answer. So I think we should go to the next question. When can reaction order be determined? So I have four options only for the irreversible reaction. The second is only in the initial stage of a reversible reaction. C is in both irreversible reaction and the initial stage of the reversible reaction. And fourth is only at equilibrium. So what do you think? What is the right answer? You can write in the chat box. You can communicate with me. Ramya, you raised your hand. Do you want to do you want to speak something, or you raised your hand? I don't know why. You can speak if you have any doubt, or you can also write. Okay, Ipshmita gave me D answer only at equilibrium. Okay, so let me try to clear this. Firstly, the answer should be C. And why the answer should be C? Let me explain you why. So, for example, again, you have A, you have then B, and this is giving you, let's say, C and D. Okay. Then, if it is a reversible, so reversible means C and D will also can give rise to A plus B. Okay, but if you know this reaction rate or the reaction, or so reaction rate have the equation, this is K, the concentration of A, concentration of B, and then these are raised to power M and these are N. Okay, and the question is, when can a reaction order, so how we can calculate this M and N? Okay, the thing is, first thing we need the concentration of reactant. Okay, and if it is the reversible change, if C and D is converting into A and B, so it will be very difficult to get to know the concentration of the reactant per unit time. Okay, so the reaction should be irreversible. The first thing is that. Okay, then only we can get to know, as you know, this is your concentration, this is again your time, and then this is your rate of reaction, right? So if this will be the reversible, then this concentration of A and B can't be determined very accurately. Okay, so we have to have the reaction that is irreversible in nature. This is right. Okay, the fun thing is, then only in the initial stage of the reversible reaction, this is again right, because in the initial stage what will happen, the C and D, the amount of the C and D will be very negligible. So whatever the concentration of A and B, we can calculate. Okay, so yes, this is again right, the initial stage of the irreversible reaction. And this both we can have in the C option. Only in equilibrium, no, we can't do this in equilibrium, because A and B will change into C and D, and C and D will be changed into A and B, and the quantification of the concentration of A and B will be very difficult. And that's why again the quantification of your order will be difficult for us. So that's why your C answer will be the right answer. Okay, here I, so in irreversible reaction, the reaction proceed in one direction. So order can be determined from reaction law. In a reversible reaction, the rate law is applicable only in the initial stage before significant amount of product accumulate and reverse reaction become significant. So that's why B answer will be your right one. Okay, coming to my next question. This is very much similar to the last question only. In a reversible reaction, when can reaction order be determined from the forward reaction alone? So forward means we are going from A to B to C to D, but we are not going from C plus D to A plus B. So this is your forward reaction. So how, but this is a reversible reaction. So how you can determine your reaction order? Can you tell me the answer for this? Can you guess something? Can you write in the chat box what should be the answer for this? Anybody? Even it is okay if you are giving me the wrong answer, because I will correct you, and you will have some memory for this. So the answer D will be right. Why? Why this is right? No doubt B is also right at some point. But as I told you, because this is the reversible reaction. So reversible reaction means A and B will change into C and D, and C and D will change into A and B. Okay. So even if it is the initial stage, there may be some probability that C and D will also give rise to A and B. Okay, so that's why this is no doubt right, but this is not very much right, because this is more right. I tell you why. So, for example, your A and B, the reaction rate of your A and B changing into C and D is, let's say, 3 hours. Okay, and then from C to D, it is taking 8 hours. Okay, so what do you mean by this? Your equilibrium lies far to the right. Firstly, when your product will be very much accumulated into C and D, then only it will move to A and B. So it will take time. So if your equilibrium it is to the right side, so what will happen? It will take time to get be reversed. Okay, but if it is the left equilibrium, so what does it mean? It means that A and B will change into C and D, and C and D will not take much time to convert back into A and B. So your this, when the equilibrium lie far to the right, so this is your more appropriate answer than the option B. So if equilibrium lie far to the right, it means that forward reaction dominates and the reverse reaction has little effect. This will allow us to approximate the reaction order based on the forward reaction alone. Okay, so these are very important question now. We have understood what do you mean by reaction rate, reaction constant, and a little bit about the molecularity. Okay, now we will expand this order reaction. Okay, so we have three type of order reaction: zero order reaction, first order reaction, second order reaction. We also have third and fourth, but we are not talking much. We are just limited to zero, one and two. And my question is, which of the following is the correct rate law for a zero order reaction? I will explain you what do you mean by this zero order, but before that you have to let me know how much you already have understanding about this topic. So based on that I have this question. So option is rate is equal to k multiply by concentration of A. Then B is rate is equal to k and concentration of A raised to power 0. C have the raised to power 2, and D has the natural log of A multiplied by the K. So let me see the answer of you people. Sheikh Sonia gave me B answer, Ramya gave me A answer, and Sheikh Sonia again gave me B answer. Dharmika also gave me B answer. Okay, yes. So yes, answer B is right. So this is K, concentration of A, and then raised to power 0. Let me tell you why. From where it was derived. So let me explain what do you mean by this zero order reaction. What do you mean by first order and second order? So based on that, I think you can tell me the answer. Whatever the question we will have in the next slide, you can tell me the answer, but firstly you have to understand what do you mean by this. Okay, so let me tell you. Okay, so for example we have a reactant, okay, and this reactant is changing into the product. And as we already have discussed, this rate is nothing but the concentration of the reactant that is changing with the time. And we know that this concentration of A will decrease over the time, and that's why we have the minus sign. So the change of the concentration of your reactant per unit time will give the concentration. So Ca is the concentration of reactant A at time t. dCA upon dt is the rate of change of concentration of A with respect to time, and negative sign is showing us that this A, the concentration of a reactant, is decreasing over the time. So this is very much clear. Okay, so we had first equation is this one. Then let's come to the next one. So what we got to know by experiment, that this rate of reaction, this dCA upon dt, is reciprocal to the concentration of reactant raised to some power, that is n, and this is called the reaction order. So here this n is nothing but the reaction order. So by experiment we got to know that we have some relation of this uh, change in the rate or change in the concentration of reactant per time. It has some relation with the reactant concentration raised to power n. Okay, and if we are doing this, like if we are removing this reciprocal, then we must have some constant, and this constant is known as the rate constant. Okay, so this is your equation that will be used every time whenever you are calculating zero order, you are calculating first order, or you are calculating second order. Okay, so if it is a zero order, then this n value will be 0. If it is the one order reaction, then this will be 1. And if it is second order reaction, then this will be 2. Okay, so we just are changing the value of this n. So from here, so if it is a zero order, then this will be K, C, A, means this is the concentration of the reactant, and then n, and here if it is a zero order reaction, then n is equal to 0, and we know that if something is raised to power 0, then this will be 1, right? Okay, okay, so this we already have got, right? Then if it is the first order reaction, then this is raised to power 1. So raised to power 1 will be Ca only. If it is a second order reaction, then this will be Kca raised to power 2. And if it is a zero order reaction, then as I told you, C0 is nothing but 1. So that's why it is just K. So if it is a zero order reaction, then this will be the equation for you. Okay. So my next question is based on this only. So if you have the first order reaction, which of the following is the correct integrated rate law? So the first is the concentration of A is equal to initial concentration of the reactant minus Kt and multiply by the concentration of the reactant. Then here we have the natural log. Here we have 1 upon K, and here we have e raised to power Kt. What do you think? For the first order reaction, which of the following is the correct integrated rate law? Can you tell me the answer for this? You can write in the chat box. Sonia gave me answer B, this one. Anyone else who want to give me that answer of this? Anyone else who want to give me the answer for this? I will drive this equation as well for you so that you have in mind what is the integrated rate law for zero order, for first order, for second order. Don't worry about this. You can also give me the wrong answer. But because if you will engage with me academically, then I think this will be good for you people, and even for me, that we both will learn together. Anyway, so B is the right answer. Let me tell you why. So okay, we already have understood this one. Change in the concentration of the reactant per time. This is rate. Okay, and if it is the first order, then this will be Kca, because here raised to power is 1. Okay, if we will arrange this, this will go here and this will go here. So what will be? dCa upon Ca is equal to minus K dt. If we will do the integration of this, then, and if we are then after integration, what we will have, this is the natural log of Ca is equal to minus kt plus a constant of the integration. Okay, but because we know that when t is equal to 0, at time t is equal to 0, our concentration of reactant was Ca0. So this is the initial concentration. Okay, and if we are putting here the initial concentration, then what will we will get here? T, because t is 0, then this value will become 0. So from this one, what we will get, that the natural log of Ca0, and this is this one, right? So natural log of Ca0 is equal to C. And if we will put this again in this equation, then what we will get? This Ca, the concentration of the reactant, is equal to the initial concentration of the reactant, E, minus K. This is the constant and this is the time. Okay, so this is your final equation. And if you want to calculate the half-life, then half-life will be nothing but the natural log of 2 upon K. And we people do know the value of this natural log of 2. Can you tell me the value of this natural log of 2? This is 0.069 something, right? 693. Okay, the thing is, this is our final equation. Then let me go further to explain you. So here, this is natural log of A. This will give you minus kT plus natural log of A naught from that equation only, right? Okay, the next question is, now you have to tell me the integrated rate law for second order reaction. So can you tell me the integrated rate law for second order reaction? 6 Sonia gave me C answer. Anyone else who want to give me the answer for this? Okay, yes, this is the right answer, and let me tell you why. Okay, so we have already learned. So this is for our second order reaction. Here, this is raised to power 2, right? And again, we will rearrange this. This will go here, this dt will go here, and this is how this equation will be like this. dCA upon C square A is equal to minus K dt. If we will do the integration and then using the formula, we will have this one. Minus CA is equal to minus KT plus C. Then again, we are here at time is equal to 0. This CA is equal to CA0. Okay, this is the initial concentration of the reactant. And based on that, we will have this one based on this equation. Then we will put again into the last page equation. Then we will get this one. And this was the question. And again, we can also calculate the time half life of your half life. If your reaction is second order reaction, then this will be 1 upon K Ca naught. So this equation will give you the right answer for your MCQ, right? This is very simple question. What is the unit of rate constant? So this is not the rate reaction, but this is the rate constant K for the zero order reaction. And this is molarity per second, molarity per second, per molarity square, and per second. What do you think? What should be the right answer for this? This is very simple, and I will explain why. How? So again, I have this reaction. Reaction is equal to your rate constant, and then you have 1 C, and here if it is 0. Okay, we have learned this, right? For the zero order reaction, what will be? It will be K, and here the concentration of your reactant, let's say concentration of reactant is Ca, and because it is zero order, then raised to power it will be 0 only. Then this R is equal to K, right? Because this is 1. This is 1. So your rate is equal to K. And you know that this rate is nothing but molarity upon second, right? So what should be the answer of this? This is fixed. The rate of reaction is fixed. The unit for rate of reaction will be molarity per second, right? But this, the unit for this K will be will be changed as soon as this will raised to 1 or this will be raised to 2. Okay, so here if this is just 1, then this K is equal to R, and the unit of this R is nothing but molarity per second. So C is the right answer. Okay, so here again you can see, as I told you, here the rate of rate reaction, that is change in the concentration of the reactant upon dt will be equal to K. Okay, and then this will give rise to, and this will be your concentration, and concentration per unit time. So this will be molarity per second. Okay, so from here we have learned this is your rate law here, because Ca was raised to power 0, so that's why this is just K. So for zero order, your rate is equal to K. Okay, for first order, your rate will be is equal to K multiplied by Ca. For second order reaction, your rate will be equal to K multiplied by Ca raised to power 2. Okay, and we also have seen the integrated form. So for zero order reaction, your Ca will equal to Ca0 minus Kt. For first order, this Ca will be equal to Ca0 e raised to power minus Kt, and second order will be Ca is equal to 1 upon Ca0 plus Kt. So this is your rate law we already have discussed, and this is your integrated form. And based on that, we have a lot of question. We will try to solve that question. So but before that, you need to establish your concept from where this rate law and integrated form came into picture, right? So I think this is clear. For zero first order reaction, what will be the rate law and what will be your integrated form. Next, coming to the next question. Okay, for a zero order reaction, which of the following plots give a straight line? So this is my plot, and if I have, and this is giving me straight line. So this straight line, or let's say this one is more right. Let me, is this. Okay, because we know that concentration will change with the time. Okay, this is very much clear. But how this will give, this can be like this. This is also the concentration is changing with the time. It can be like this, very much like this. The concentration is changing with the time. But when it will give to the straight line for the zero order reaction, will it be the natural log of A? This is A, let's say, concentration of reactant. This is A for this case, and this is A. So whether it should be the natural log of A, or it should be 1 by A, or it should be A square, that will give you the straight line for the zero order reaction. What should be, how we should plot so that it will give us the straight line? Can you tell me the answer for this? For zero order reaction, which of the following plot gives a straight line for zero order reaction? This is just for example. I'm not saying this is the right answer, but this is just the example that concentration of your reactant will change with the time, and that can give you any type of curve. It may be a straight curve, it may be quadratic in nature. So you have to tell me, for zero order reaction, how we have to plot the concentration of A with the time so that it will give you the straight line. So let me tell you, let me explain. If Smita gave me B answer, yes, this is the right answer. And how this is? So, okay, we already have learned this reaction is equal to K multiplied by the concentration of reactant raised to power 0. And we know that this is nothing but 1. Okay, so rate is equal to K. So here what we can say is change in the concentration of reactant per unit time, because this is nothing but this is the rate, is equal to K. Then this dA is equal to minus K dt. Okay, and if we will do the integration of this, And then what we will get, this A, concentration of your reactant, will be concentration of reactant, initial concentration of reactant minus Kt. And from here you can see, uh, so what will you do? This will be your Y, this will be your X, and here the slope value will be your K minus, and this one is your intercept. So let's say it is starting from here, so this is your intercept, so this is your A node. So initially your concentration of reactant was higher, and then this is reducing with the rate, with the slope minus K. And so what you go to, and this is nothing, this is just Y is equal to A plus BX, right? So if you are having this Y and X on a Y and X grid, then this will give you the straight line, and this will be your intercept, this will be your slope as slope. And just like that, if you have zero order reaction, then this will be your equation we already have learned. And this A uh, is at the Y axis, this T will be your X axis, K will give you the slope, and intercept will be the A node. So if you will plot this T versus the concentration of A, so plot of A versus T is a straight line with the negative slope for the zero order reaction. But this will change when we will when we will change the order of the reaction, right? But for the zero order reaction, your final equation will be this one only, and based on that, this A and this T will give you the straight line. Is it clear?
Yes, ma'am.
Thank you so much for your feedback. Okay, the next question is, if we are having this natural log of A versus time, and then it will give you this straight line. So what type of order reaction we are talking about? So whether it is zero order, first order, second order, or third order reaction. We already know that for the zero order reaction, the graph should be, this should be A and this should be T. Then only this will give us the straight line. So this is not the answer. A is not the answer, because we already have understood this from here. This A. Okay. So now can you tell me which reaction order will give us the straight line plot when natural log of A is plotted against T? You have three options now: first order, second order, third order. You can estimate, you can guess something. Let's say it is not the negative marking question, right? So you will not get the negative marks for the answer that you will give. So you can give me any answer, I will correct you, don't worry about this. Sonia, tell me, this is the first order, ma'am. Okay. Okay, let me. Okay, yes, this is first order. And how this is first order, let me show you how. Uh, Again, we already know about this. We have talked a multiple time about this. Rate is equal to K multiplied by A. This is the concentration of reactant raised to power 1. And this rate is nothing but change in the concentration of the reactant upon time. And this will equal to Ka. Then we will rearrange this. After rearranging, what we will get, dA upon A is equal to minus K dt. Then we will do the integration, and after that, what we will get, this natural log of A is equal to minus Kt plus natural log of A0. So this is the initial concentration, right? So this will be your equation. So this is again just like y is equal to A plus bx, right? So what you will do, if you are plotting this against this, then minus k will be your slope and this will be your intercept. So for your first order reaction, this natural log of A raised to power t will give you straight line, and here your slope will be minus k, and here your intercept will be natural log of A node. So this is the initial concentration of your reactant. So based on that, your B answer should be correct. Is it clear? So for first order reaction, there should be natural log. For the zero order reaction, it was just the concentration of the reactant, right? Just keep in mind. Okay, the next is, if you have the second order reaction, then what kind of plot will give you the straight line? We already have talked about this. This was for the zero order reaction, right? So this will not be the answer. This we already have talked about. This was the first order reaction. So this again will not be the answer. You have just option C and D. So what should be the answer for this? 1 upon A versus T or A square versus T? What should be the right answer for this? Yes, the answer should be C. I will tell you how. Okay, this is the equation at very initial stage, that rate is equal to K multiplied by concentration of the reactant raised to power 2. Okay, and we know that rate is equal to nothing but change in the concentration of reactant upon time, and this is equal to K multiply A raised to power 2. We will rearrange it, then we will do the integration, and after integration, this will be our final equation. 1 by A is equal to KT plus 1 by A0. So again, if we will plot this with T, then what will we will get the linear. So 1 upon A, and this is T, then we will get the straight line. And here again, K is our slope, and the intercept will be 1 upon A node, right? So you got plots for first order, for zero order, and for the second order, and you got to know the equations. From that equation, how we can plot our straight line plots from y and x as per the equation that we already have seen, right? Okay, so you have seen the slope of each of this first order, second order, and zero order reaction. Now you have to tell me which of the following statement is true about the slope of the linear plot for different reaction order. The slope is always negative. The slope is positive for first order reaction, but sorry, the slope is negative for first order reaction, but positive for second order reaction. The slope is positive for zero order reaction but negative for the first order reaction. Slope is always positive. What do you think? What will be the answer? Slope of the linear plot for different reaction order. Which have the positive slope, which have the negative slope? Can you tell me? So see here. Um, So for the zero order, this was negative minus k, right? Then we talked about our first order reaction. This was again minus k. For second order, this was positive k. So now can you tell me the answer for this? Ipshmita gave me answer B. That slope is negative for the first order but positive for the second order. Yes, this is right answer because we already have discussed, right? This is, I think, very essential for you. So if you have zero order reaction, this will be your equation. And based on that equation, this will be your concentration and this will be your time and this will give you the straight line. Okay. If you have zero order reaction, then this will be the natural log of A. This natural log of A versus time t will give you the negative slope. Okay. Then if you have the second order reaction, this will be 1 by A and this is time and this is giving you the positive slope. Okay, and this we have summarized here. This is integrated law. We already have discussed linear plot uh, and then slope. Here, negative slope is for zero order and first order. For the second order, this is giving us the positive slope. And what will be the interception? So I think this is the summary from where you can get your linear plot, you can get what will be your slope, what will be the intercept for first order, for zero order, and for the second order reaction. Right? I think this is very much clear from like my point of view, but I don't know how much you are understanding. But this is the whole crux of first order, second order, and zero order reaction. And based on that, you will have some numericals and you will solve it. Okay, let's move to the next question. Okay, so this is the question very much similar to your assignment question. I think only the value has been changed. So if the rate constant for the first order reaction is 4 per second, find its half-life. So how you can calculate the half-life for the first order reaction? So for the first order reaction, the half-life is nothing but is equal to natural log of 2 upon upon the upon the k. This is your rate constant. So now can you tell me the rate constant for the zero order reaction is 4 per second. Now can you calculate the half-life? As I told you, the value of this natural log of 2 is approximately equal to 0.693. Then I think you can calculate the half-life. So let me tell you the answer. The answer will be 0.17, and how this will be, let me share with you. Okay, so this half time is equal to natural log of 2 upon k. Natural log of 2 is equal to 0.693. K is given, that is 4 per second. If we will substitute the value, then half-life will equal to 0.693 upon 4, and this will be equal to 0.17 second. Okay, so your answer A is the correct one. So this is how, if this is the first order reaction, then this is the formula. But if it is a second order or zero order reaction, this formula will be changed. Okay, and I already have shared you the formula in my slides. So I think this is how you can solve your first assignment question using this formula. Okay, then I already told you the order of the reaction. You can't calculate from coefficient. You have to do some experiment, and based on that experiment, you can calculate the order of any reaction. Okay, so here it was the experiment. So after some time, after very initially when time was 0, then after 1 hour, after 2 hour, after 3 hour, they measured the concentration of the reactant, and the concentration of reactant was changed from 120 to 72 to 43 to 26 to 16 to 5.5. Okay, and then the question is, from this, first determine the order of the reaction. First you have to tell what is the order of the reaction, and then you have to calculate the rate constant. So how you will calculate this? Naveen, you raised your hand. Do you have any query related to this question or something? Then you can tell me. Naveen, you raised your hand. So how you can calculate the order of the reaction? So the thing is, as we know, this is our concentration of reactant, and this is time. So if this is time, right, and this is concentration, if this plot give us, if this plot will give us this straight line, then we will tell that this is the zero order reaction. If we will do the natural log of this concentration A, and then if we are having this straight line, then we will tell that this is the first order reaction. But if our plot is like this, 1 upon A and then T, and if this is giving us the straight line, then we will tell that this is the second order reaction. So with the time, so we have the time, we have the concentration. So first you will try to plot this graph. If this is giving you straight line, then we can tell that this is the zero order reaction. If this is not giving you the straight line, then first you have to convert your concentration into natural log of the concentration, right? And then try to plot it with the time. If you are having the straight line, then this is the first order reaction. Even then, if you are not having the straight line, then just change your concentration to reciprocal of the concentration, that is 1 by A. So you plot 1 by A to T, and then see if this is the straight line graph you are having or not. If you are having the straight line graph, then you will tell this is the second order reaction. So the first thing is, you have to see the graph. What kind of graph is giving you the straight line? If it is the A versus T, whether it is the natural log of A versus T, or it is the 1 by A versus T. Based on that, you can tell what order of the reaction you have. If it is A versus T, then this is zero order. If it is natural log A upon T versus T, then this is the first order. If it is 1 upon A versus T, then this will give you the second order. So from this table, you have to see what kind of order it is. Okay, and based on that order, so for example, your rate, so for example, this is your first order reaction. Okay, and you know that for the first order reaction, this is the rate is equal to K multiplied by the concentration. Okay, and based on that, you can calculate the SI unit of your K, that is the rate constant. You know the unit of the unit of this rate reaction is what? Molarity per second. This is again molarity per second. So what will be the, so this is R upon, okay, so here molarity per time. This is molarity per time. So this is molarity per second, right? And this concentration of C is nothing, A is nothing, but this is molarity. So the unit for K will be per second, but provided if it is the first order reaction. So let's see what will be the answer for this? So it is first order reaction, and let me tell you, for the first order reaction, your rate constant unit will be uh, time per time. Okay, so like if I'm very much naive and I don't know like what will be the answer for this, but just keep in mind that if the unit is per second or per time, or let's say per hour, okay, so this unit is the first, or this unit is for the rate constant, and this unit uh, is of the rate constant when your order is 1. So this can't be second order. So C and D is not among the right option, because every time the rate constant unit for rate constant unit, if it is in per time, then this will be just for first order reaction, right? Then answer will be among this one, A and B, and then you have to calculate this the value of this constant. So how we can do this, I tell you. So first what we did is, we have time, we have concentration, then we calculate the natural log of C concentration, and when we plotted this natural log of C versus T, that gave us the straight line. So from that we are confirmed that this is the first order kinetics. Then and here the slope is minus k, and from that slope value, whatever the slope value we will have, this slope value will give you the rate constant. Okay, because here r is equal to k, right? Minus k. So for whatever the rate value, slope value you will have, that slope value will give you the value of the k, and this is how you can have the k is equal to 0.35 per hour. I think this is clear how you can calculate. Okay, next question is again from your assignment, but the value has been changed. And here you have the first order decomposition. Just keep in mind, this is first order. Then what they did is, your rate constant is changing at a different temperature. So when your temperature is 290 Kelvin, your rate constant is 3.25 into 10 raised to power minus 4. When your temperature was 300 Kelvin, that your temperature rate constant was 1.22 into 10 raised to power minus 3 per second. And because this is first order, then please see the unit of your rate constant. This is per second. Okay, then you need to calculate the approximate activation energy for this reaction. So you have just very simple formula how you can calculate this. I show you. uh, okay, so based on this Arrhenius equation, natural log of K2 upon K1, so this K2 and K1 is your rate constant, is equal to activation energy upon R. This R is gas constant, multiplied by 1 by T1 minus 1 by T2. Everything is given. This K1 is given, K2 is given. We know the value of the gas constant. We just need to calculate. We just need to calculate this activation energy. Everything is given for us. This 2 rate constant is given, and this 2 temperature is given. We already know the value of this R. We just need to calculate the activation energy. So first what we will do, because this K2 upon K1 is the natural log of K2 upon K1. So first we will solve this. We will put the value here. This K2 and this K1, and this is how this is nothing but this is 1.32, right? Then we will compute 1 upon T1 minus 1 upon T2. We have this value, and then this is how we will get 0.000115. We will put into that equation this 1.32 is equal to activation energy upon gas constant multiplied by this one. Okay, and this is how we will rearrange the equation and we will calculate EA, that is the activation energy, and this will be 90 kilojoule per mole. So the answer C will be right, that is 90 kilojoule per mole. I think this is clear. Should we go further? Is it clear? This was nothing but a very simple formula. The formula is natural log of K2 upon K1 is equal to activation energy upon a constant multiplied by 1 by T1 minus 1 by T2. So based on that formula, we can calculate the activation energy. Okay. Most of the question is based on your zero order, first order, and second order reaction. We already have completed like basic concept of our first order, zero order, and second order. So I think now you can tell me the answer very rapidly, because we already have cleared the concept of this order reaction. Now, our reaction is x plus 3y is giving us the product. The rate of reaction is giving, and the concentration of x and y is also giving, that is 0.25 molarity, sorry, and rate constant is also giving, and this rate constant is at 350 Kelvin, and this is 2.5 into 10 raised to power minus 2 per second. Okay, per second. Can you tell me this is the unit of your rate constant when the order is what? Zero order, first order, or second order? Yes, it's Smita. This is like from only rate reaction, you can tell what kind of reaction order it will be. It will be first order, but this is just the clue. Okay, but you have to tell me the overall order of the reaction. How you will calculate this? We know, let me clear this. We know reaction is equal to K and then the concentration of your reactant upon M, or let's say this is your A and this is your B. And this is the order of your reaction. So overall order of the reaction will be nothing but M plus N. So A is nothing but X, B is nothing but Y. Okay, and the concentration is given. So for this is 0.25 and this is 0.25. This one is also giving, rate constant is also giving, and this rate of reaction is also giving. So based on that, we will calculate M plus N. And whatever the M plus N we will have, that will give us the order of the reaction, right? Everything is given, just M and M is not given, and we need the sum of M and N because that will give us the overall order of the reaction. This is the formula, right? So how we can solve this? Let's see. So this is our rate. That rate is equal to K multiply by the concentration of your reactant X and Y, and here raised to power M and N. And if we will add up this will give us the overall order. Everything is given, right? This one is given. Then we will solve this and we will get to know that 0.2 is equal to 0.25 raised to power N plus M. And this 0.5 is very much similar to 0.25. And here this raised to power is 1. So what I can say, this M plus N plus M is equal to nothing but 1. So this is the first order reaction. There is a second approach how we can go. We can also go with the natural log and log. Here it is not mentioned. I think in the next question we already have mentioned. But here N plus M is equal to 1. If this is 1, then overall order of the reaction is 1. That is the first order. Okay, so this is how we can calculate our order of the reaction. If the concentration of your reactant is given plus the rate of the reaction and the rate constant is given, then you can calculate the overall order of your reaction. Okay. The next question is, the rate law is given involving three reactant A, B, and C, and this is your rate law. This rate is equal to K, that is rate constant, multiplied by the concentration of A raised to power 2, concentration of B, concentration of C raised to power 3 by 2. Then we need to calculate the rate of reaction change. But when the concentration of A is half, then this will A by 2, and the concentration of C is double, then C will be 2C. Then how this rate of reaction will be changed? So my option is increase by 2 by 3, reduce by 2 by 3, increase by 3 by 4, reduce by 3 by 4. What do you think? What should be the answer for this? Can you estimate it? So we have one original rate and then we will calculate the new rate. Okay, but new rate in the form of original rate. Okay, and then we will see what is the coefficient that we have to multiply so that we can have the original rate from the new rate. Okay, or let's say from original to new or new to original. So how we will do this? Let's see. Okay, so this is the equation that we already have given, that this is the rate law. Okay, and if the A is halved, then A by 2, C is double, that is 2C. Then our new rate will be, here we will replace this A with A by 2, and here we will replace this C to 2C. Okay, and then what we will do, we will try to change this into this, but with some factor. Okay, and that factor will tell like how this new rate has been changed as per the original rate. So how we can do this? I think the next slide will give you some clarity on this. Okay, so if we will calculate this one, this A by 2 is equal to A square upon 4. So this is A square. We just need to divide it by 4. And this here, this is 2. So 2 upon, let's say, 4, right? And then here we have 3 by 2 as well. So this will again give you some more magnitude. So what we will get? So new rate will be K, A by 2 by 4, B, and we have multiply this 3 by 2 to, so this 2, 3 by 2. So this will be 2.83 and then this one. Okay, so we will exclude this and this from the equation. So this will come out and this is our original rate. Okay, so this is our original rate, this is our new rate, and so new rate is approximately equal to 3 by 4 into original rate. And this is how D option is right, that your new rate is 3 by 4 of the original rate. That means it has been reduced by 3 by 4. So this is how you can solve your question. Okay. The next question is, you have one equation that is Cl2O7. This is giving you Cl2 plus O2. Okay, and here the pressure, initially pressure is 0.08. Then after 1 minute, the pressure has been reduced to 0.04 atmosphere, and you need to calculate the rate constant. So what you need to do is, wherever there was the concentration, initial concentration and the concentration of reactant in your first order reaction, you have to replace it with the initial pressure and pressure. Okay, pressure of the reactant. So this is how you can solve this question. So let me tell you how. And this is first order reaction. So we already have discussed for the first order reaction, this is our integrated form of the first order reaction, that C is equal to C0 E minus KT. C is the concentration of the reactant after some time T. Then C0 is the initial concentration at time is equal to 0, and E minus KT. KT is after that time you are calculating the concentration. But here we are replacing this concentration with the pressure. And based on this, the k will be minus 1 upon T natural log of C upon C node. Okay, and everything is given. C node is given, C is given, T is given, then rate constant you can calculate. Okay, and your rate constant will be minus 1 by 16, natural log of 0.5. And so this k is equal to 0.1155 per second. Please see here the unit of your first order reaction, rate constant. So this is per second. So the answer will be whatever the options I have given. So based on that, the nearest was 1.16. So that's why this will be your right answer. Okay. The next question, again this is very much a simple question. So the question is, please give me 1 minute. Okay, the question is, you need to find out the rate low. You need to find out the rate low when you did some experiment, and after that experiment your x was this much, your y was this much, and this x and y are the reactant, right? And this is giving you product y, and your rate is this much. So but this here, as I told you, this r is equal to nothing but k. This, let's say a, this is x here in the case, and here it is b, but here it is the raised to power m and n. And this we can calculate experimentally. This is not the coefficient, this is not 2 and 1. This is you can calculate, you have to calculate experimentally. So how we can do this? So based on this, if we will know the value of m and n, based on that we can tell which option is the right one, right? So how we can calculate the value of m and n? So for example, here y is the constant. So if y is the constant, then y will be cut out. So let's say this will be cut out, then this will give us the value of m. Okay, here this is constant, x is constant. Then if we will do the ratio, then what will happen? This will give us the n value. So let me show you how we can calculate this. So what we are doing is, firstly, we know this is our equation. Rate is equal to k xy, and this xy will be the like raised to power m and n. Okay, and if we are doing r3 upon r2, so here x value is constant, so this is 0.6 and this is 0.6, so this will be cancel out, and here the value is changed, 0.10 raised to power n and 0.05 raised to power n, and rate is also given in that. So rate is also given, rate is given, this is given, but this was the constant thing. Okay, so what we can do is, so from here what we will get is, this 2 is equal to 2n, so this n will be 1. Okay, and here we can also calculate it using the log, but if 2 is equal to 2n means n is equal to 1, so you got n is equal to 1. Now you need to calculate the value of m also, then only you can give the reaction law. Okay, so Then we will have the ratio of rate 2 upon rate 1, and here this is same, this will be cut out, and this again 2 is equal to 2m, so this m will be equal to 1. So your m is equal to 1, your y is n is equal to 1. So this is how the rate will be k, x and y, and here it is 1, here it is 1. Then this is nothing but this is the second order reaction, because 1 plus 1 will give you 2. So this is our second order reaction, but the final rate law is rate is equal to k x multiplied by y. This is how we can calculate this question. Okay, this is again very much very simple question actually. So the rate of appearance of C oxygen. So from O3, the O2 is being generated. So the rate of appearance. So this, and we know that the unit of rate is nothing but the molarity per second. So this is our rate. Okay, so rate of appearance of oxygen is 0.240. So this is our rate of the reaction. This is our time. How much oxygen gas will be formed during this time? So how you can tell me this one? So let's see how we can calculate this. Very much simple. We know that the rate is equal to change in the concentration of the reactant, or let's say product, upon time t. Okay, so concentration, change in concentration of oxygen is equal to rate multiplied by dt. This rate is given, this dt is also given, then change in the concentration of O2 you can calculate to multiply this rate with the dt. So this is how you will get the answer. The concentration of oxygen formed in 2 seconds is 1.44 molarity. Okay, because this is the concentration, and always the concentration unit will be molarity, and molarity is nothing but the number of mole per liter, right? So this is how we can calculate this type of question. Okay, now the chemical contaminant in groundwater undergoes first order degradation with the half life of 200 days. Initial concentration of the contaminants is also given, that is 50 microgram per liter. How long it will take for the concentration to decrease to 10 microgram per liter? So this is our initial concentration, C node or C0. This is C. This is first order reaction, and the time, half time, that is 1 by 2 is also given. So what you need to calculate is time t, and this is first order reaction. So what will be your so first thing, you should remember the integrated form of your first order reaction. Based on that you can calculate this. Okay, the thing is, we know that the first, this half life is nothing but equal to 0.69 upon k, that is the rate constant. If we have the half life, then we can easily calculate this rate constant. Okay, and if we know the rate constant, if we know the C and C node, then putting everything into the integrated form of your first order, we can have the value of T. So let's see how we can calculate this. If you have any problem, if you are getting boredomness, then you can tell me. I can I can give you some time so that you people learn it very efficiently, right? So how we can do this? Let's see. First, we will calculate the rate constant. And how we can calculate the rate constant? This rate constant is equal to natural log of 2 upon half-life. We know the natural log of 2. This is 0.693 upon 200, and this is how we calculated the rate constant. Then we will put this rate constant here in this equation. This is the first order decay reaction, or the integrated form of your first order. C is given, C node is given, K we already have calculated, T we need to calculate. So we have to put everything into this equation. So if we will put this, then what we will get? So C upon C node is equal to E minus KT raised to power minus KT. Uh, C is equal to 10, C0 is, or C node is equal to 50, and this is how we will calculate this. Point 2 is equal to E raised to power minus 0.00347 into T. If we will do the natural log on both sides, then we will remove this E, and then this is how we can calculate this T value, and this T value is equal to 432 days. So this is how we can calculate how much time we need to change our concentration from 50 to 10 molarity. Okay, so this is how we can calculate this. Okay, next question is again very simple and very much similar to the previous question only. So you have one pesticide that is degrading in the soil, and that degradation is following the first order kinetics. And again, the half life is given. This is 20 days. What fraction of the initial concentration? So you need to calculate C upon C node. So what fraction of initial chlorpyrifos will remain after 100 days? So here T is equal to 100. And this is the first order reaction. So again, firstly we will calculate the rate constant K. We will put that rate constant into our integrated form of first order reaction, and then we will calculate this C upon C node. So how we can do this? Let's see. So again, first we will calculate the value of K. So this K is equal to nothing but the natural log of T upon half-life. Half-life is 20, that is given. Then this is how we can calculate the rate constant. So rate constant is 0.0347 per day, right? And then most of our job is done. What we will do, C upon C node is equal to E minus KT. This is the integrated form of your first order reaction, and everything you have to put your T value. We know the K value we already have calculated. Then this is the fraction of your pesticide concentration that will remain, and this is 0.031. This is how we can calculate, right? So I think this is again clear, and these questions are very much similar to your assignment question, just the value has been changed. Okay, this is most of your question is related to first order reaction only, and if you know the integrated form of your first order reaction, if you know the half life, how we can calculate the half life of your first order reaction, then most of your job is done. You can calculate everything very easily. So here this is first order degradation of pollutant in your water sample. After 40 minutes, this concentration decreased to 30 mg per liter from your initial concentration. So your C node was 80 mg per liter. Your C, after time T, your concentration is 30 mg per liter. After 40 minutes, so your time is 40. And this is first order reaction, and you need to just calculate the rate constant, that is K. So how you can do this? Can you tell me how you can do this? You just need to calculate the rate constant. So let me tell you how we can do this. Okay, again you have this equation, integrated form of your first order reaction, that is C is equal to C node E raised to power minus KT. You have C node, you have C, K you need to calculate, and you have T. So you will put everything into this equation. Natural log of C upon C naught. So this is 30 upon 80 is equal to KT, that K we need to calculate, and T is equal to 40. And then this natural log of 0.375, and then this is how you will calculate the value of K, and this K value will be 0.045 per minute. Please again see the unit of your rate constant. This is per time. So this is how you can tell this is the rate constant for your first order reaction, right? So this is how you can calculate this question also. If you have any problem, anytime you can write in the chat box, you can speak. I will try to solve your query, right? Okay, again, this is the first order reaction. Most of your reaction is first order reaction. So that's why most of your question is based on only first order. So what the question is, a first order reaction is 40% complete. 40% complete means 60% is remaining. Okay, so your concentration, initial concentration, let's say it was 100, then your C is equal to 60. Okay, your 40% reaction is completed in 50 minutes. How much time will it take for the reaction to be 80% complete? So 80% complete means initially it was 100, but right now it is 20. Okay, so if your C node is equal to 100, your C is equal to 20, and time is 50, but for this one. So how you can calculate the time for this one? From changing from 100 to 20 concentration. And if this is the zero order, so how we can do this? Again, with the same formula. So from your first order reaction formula, K is equal to, because we have the E value and E value, if we are changing this E value, then this will be 2.303 upon K log of A upon A minus X. So A minus X is nothing. So this is the initial concentration minus amount reacted. So this is the remaining amount. So this is just like C, and this A is nothing but, let's say, C node. Okay, this is just the changed form of your integrated first law reaction, right? Then everything you will put, then you will have the K value. So from here, from the first thing, when your reaction is from 100 to 60, from here you will calculate the K value because T is given already. Okay, then you will calculate the K, and then you will put this K into the next equation. What happened? Okay, so K is calculated. Then what you will do? K is calculated. Then for 80% completion, you will calculate the T. Okay, you just need to again put every value into that equation only, and this is how you will calculate the T. Okay. If anything is not clear, then you can tell me. Okay. Again, for the reaction, here reactant A is giving the product B. It is observed that when the concentration of A is double, when the concentration of A is double, the rate of the reaction increase by the factor of 4. The order of reaction with respect to A is what? So you have to tell me the order of the reaction. So what you need to do is you just need to calculate M and N. and if you will add that m and n, that will give you the order of the reaction. So how you will calculate this m and n? Because the rate is given now. I think my pen is not working. Something is happening. Are you people able to see my slides? Okay. Because my pen is not working, so I just have to show you the solution without explaining much. So how you can do this? So you know that rate is equal to K rate because here we have just one chemical species for the reactant, that is A. So A raised to power n. So this is our general form of the rate law. Okay. And for the initial rate, this R1 is equal to K multiply by A raised to power n. But because when Ka is double, so if we will double this, then the concentration will be 2A, right? If it will be the 2A, then this R2, this will give the new rate 4 times. This is already given in the question that your new rate will be 4 times. So your R2 is equal to 4 multiplied by R1. This is given in your question. If you will put everything here, because your new rate is when concentration is double. So here this is 2an is equal to 4k an. So you are what you are doing, you are just putting the values. So from here you will get is this k and an will be cancelled out, because this is common in both left hand side and right hand side. Then this 2n is equal to 4, and then n will be 2. So n, if n is equal to 0, then it means this is giving you the second order reaction, right? So this is how you can calculate. This is again the question of activation energy, and we have just one formula by which we can calculate the activation and energy and the reaction rate. So how we can do this? So here the question has an activation energy of 25,000 calorie per mole, and the specific rate constant of 1.5 per minute at temperature of 30 degree. So the rate constant is given, that is 1.5 per minute. Temperature is given 30 degree Celsius, but you have to tell uh, what will be the approximate specific reaction rate constant at 10 degrees Celsius. So you have two temperature, T1 and T2. So T1 is 30, T2 is 10. You have activation energy. That activation energy is 25,000. You have the rate constant. One rate constant you have. The second rate constant you have to calculate. Okay. So we have just one simple formula. And this simple formula is natural log of K2 upon K1 is equal to activation energy upon gas constant multiplied by 1 by T1 minus 1 by T2. And just put everything, you just need to calculate K2. That is the final rate constant that we need to determine. But just keep in mind, this T1 and T2 should be in Kelvin, not in Celsius. Okay, so first you have to convert this T1 and T2 into Kelvin, and then put everything into that Arrhenius equation, and this is how you can calculate the value of K2, right? If you have any problem, you can tell me. Otherwise, this is how, like, we will put everything into our one equation, and then we will solve step by step, and this is how we will calculate the K2 value. This is the rate constant when your temperature is this 10 degrees Celsius, right? Okay, this is the next assignment question. Just I changed the value of this. So the decomposition of hydrogen peroxide in the presence of catalyst follow the rate expression, and this rate is equal to K multiplied by the concentration of your reactant multiplied by the concentration of catalyst. K is given, means rate constant is given, and at 10 degrees Celsius, and this rate constant is increased to 2.31 into 10 raised to power minus 4 at 40 degrees Celsius. So initially when we had the 10 degrees Celsius, our rate constant was something, but at 40 degrees Celsius, our rate constant has been changed and it has been increased. Then you need to calculate the approximate activation energy for this reaction. Again, we have very much simple equation for the Arrhenius. This is the Arrhenius equation or the formula by which you can calculate. Uh, you have K1 and K2. You have T1 and T2. You have the gas constant R, and you just need to calculate the activation energy, right? So yes, this is the formula. We already know this natural log of K2 upon K1 is equal to activation energy upon R multiplied by 1 by T1 minus 1 by T2. And if we will put everything into that equation, we will have the value of activation energy, that is E1. Okay, I think the answer of this you people can give me, because this is not the numerical question. Now I'm expecting, I have 3 or 4 questions and I'm expecting the answer from you, because these are not the numerical question at all. So according to Beer-Lambert law, the absorbance of a solution is directly proportional to only the thickness of the solution, only the concentration of the absorbing species, both the concentration and path length of the solution, only the intensity of the incident light. What do you think? What should be the answer for this? First, you have to know what do you mean by this Beer-Lambert law. So Beer-Lambert law says that we have a light source and we have the solution. So the concentration of the reactant or the concentration of any chemical species, if it is higher, then absorbance of that light will also be increased. Okay, so now you have to tell me. So this is the Beer-Lambert law. Absorbance is directly proportional to the concentration of your chemical species. Now you have to tell me this absorbance of a solution is directly proportional to what? Not only the concentration of the absorbing species, but also the path length. C is the right answer. Let me show you how. So we have one formula according to Beer-Lambert law, that A is equal to epsilon Cl. So this A is the absorbance, E is the molar absorbability, C is the concentration of the absorbing species, and L is the path length of the absorbing medium, and this is in centimeter. So this is the formula uh, uh, derived from the Beer-Lambert law. A is equal to epsilon Cl. And here, if we will see, this absorbance is proportional to the concentration and also the path length. So that's why this absorbance increase if either the concentration or path length increases. And that's why this will give you the answer here C, both the concentration and the path length of the solution. Right? Okay. How many functional group are present in 2,4 dinitrophenol? How many functional group? How many functional group? One functional group, two functional group, three functional group, and four functional group attached to the phenyl ring. Can you tell me the answer for this? Dinitro. So means you have two nitro group, right? and phenol. Oh, sorry, my animation was on, so that's why this balloon goes on. And phenol means you also have the hydroxyl group, right? So you have three functional group, two dinitro group, and one is hydroxy group. So the answer C will be right. So you have hydroxy group, that is OH group, and two nitro group at position 2 and 4. So that's why the answer is you have three functional group in 2,4 dinitrophenol. This is very much simple question. I think you, every people, every student should give me the answer for this. The unit of rate constant for the first order reaction is what? Rate constant. We already have calculated this. No, not Smita. No, this answer is per time, right? We calculated it. Rate is equal to K multiplied by concentration, because concentration is raised to power 1. So this will be the concentration. We know R, that is rate, is equal to molarity upon time. Okay, so molarity upon time is equal to K, and C is the concentration. K is the molarity. So molarity upon time is equal to K multiplied by molarity. So K is equal to per second. So this is how first order reaction. In the first order reaction, the rate constant unit will be per second. We already have calculated this, right? So this is how we calculated. This rate is equal to KAN, and then we know the rate has the unit of concentration per time, and concentration has the unit of mole per liter, and this is how the unit of K will be per second only, right? So this is these were all question, I think, that we had in the assignment. This question is not that much important because you people can give me the answer for this. Okay. What is the major product when 2-nitrophenol is reduced using NaBH4? What major product you will get when this 2-nitrophenol will be reduced? If it is the reduction, then this nitro group will change into the amine group, right? So what will happen? This will give you the 2-amino phenol, because this is the reduction now. So reduction means this nitro will be changed, this O will be reduced with the H, so this nitro will be changed into the amino. So 2-amino phenol. So B is the right answer. Okay, these are very three question we have, very simple question without any numerical. You just need to tell me the answer, and then we will go. We will. I have my mess timing. I will go for the dinner. So, according to the Von Hoff rule, how does the reaction rate change when the temperature is increased by 10 degrees Celsius? What will happen to the reaction rate change when the temperature will be increased by 10 degrees Celsius? It remains the same, it doubles, it triples, it decreases by half. So Von Hoff rule says that uh, our reaction rate will be doubled for every 10 degree Celsius increase in temperature, because high temperature provide more energy to the reactant molecule, and this is how this will increase the frequency and effectiveness of your collision, right? So this is the Von Hoff rule. This is very approximate. This is very approximation that if we are increasing 10 degrees Celsius, then this will give rise to the doubling of the reaction rate. Okay, this is based on spectrophotometry. So we have the name of the scientist and their contribution. So light source. So who invented the bulb? Who talked about the dispersion of light? Who talked about the photometer? And related to the scientist name. So can you tell me A, B, C, D? Who invented light source? Who talked about dispersion of light? Who talked about photometer? So a very simple guess is Newton talked about the dispersion of light, right? And here, if we will see, the only option A has such kind of hierarchy. So A is the right answer. Okay, we know the spectrophotometer, right? So we have some tubes. In that tube, we will have the colored solution, and this higher the color, high the concentration, high light will be absorbed. Okay, so this is something we will do in the spectrophotometer. So based on that, we can calculate the concentration of our chemical species. So what is the primary function of the spectrophotometer? To measure the intensity of emitted light, to separate light into different wavelength, to measure the absorbance and transmittance of a sample at specific wavelength, or to produce monochromatic light. So the main role of spectrophotometer is to measure the absorbance, because this absorbance is directly proportional to the concentration of your chemical species, right? So we need to calculate the absorbance. So this is how C is the right answer. If you will see here, uh, this is our light source. This is monochromator, because light source will give you a range of wavelength of your light. Then this monochromator will give you just one wavelength light. Okay, and then you have the cuvette. This is the tube in which you have the colored solution. Then what will happen? Your light will be absorbed by this color solution, and this will, based on the absorbance of the light, it will tell you the concentration of your sample, right? So this is the principle of the spectrophotometer. uh, which of the following is not found in spectrophotometer? So this is the thermometer, because we have the light source, we have monochromator, and we also have the sample holder. So D will be your right answer, right? Then which law is commonly used in spectrophotometer to relate absorbance and concentration? We already have talked about this. So Beer-Lambert is the law that we commonly use, because the concentration is directly proportional to the absorbance of the light that the sample will absorb. Okay, and based on that law, our spectrophotometry is the principle of spectrophotometry is like this only. Okay, which of the following factor does not affect absorbance in spectrophotometry? Because we already have learned that absorbance is equal to epsilon and this CL. C is the concentration, L is the path length. Okay, so so volume of the solution is the only factor that doesn't affect absorbance. We already have so the formula, right? And this is how we have completed our week 2. Again, we will meet on Monday from 6 to 8. If you have any query, any suggestion, you can tell me. And if you have any doubt, anytime you can mail me on my mail, that is Jyoti 21, that is 21 at the rate iiserb.ac.in. So if you have any problem, any doubt, any suggestion, you are welcome to write in the chat box, to write on my mail. You can anytime speak, and I will try to solve your question. Right. So thank you so much. We will meet again from 6 to 8 every Monday. Thank you, everyone. Thank you, Ankita. So you people can leave now.